Hello, welcome to CADinBIM MasterClass. My name is Lucas Chacha and I'm a civil engineer by profession. In this session, we are going to look at foundation, part one of it, where we are going to just look at design of reinforced concrete, part one. Part two and three will follow suit, so stay tuned, watch, like, and comment as we share these insights. Having said that, let's dive in. So foundations are basically used to transfer the structure load into the ground. So this is how you can have load from the slabs, from the beams, from the columns, and they are being transferred to the foundation. And then now from this foundation, transfer them to the soil. So let's just proceed. Now we have type of foundations. This is a shallow foundation and the other one is a deep foundation. As I had just mentioned, types of shallow foundation, and these are basically pile foundation forms majorly part of the deep foundation, or is the major type of a deep foundation type. So take load to deep level to rest on soil with higher bearing capacity. So if maybe you are working soil that is not stable or do not have sufficient bearing capacity, you need to go deep in the soil. By going deep, you can drill this pile sheet to reach the hard bearing soils with the sufficient soil capacity. So quickly, we just have an images of pad foundation. These are it looks combined footing, strip footing, mat footing, or mat foundation. Those are the type of shallow foundations in illustration format. Then we have pad footing can have a square for square column, mostly rectangular for rectangular column. However, square column can as well be used where we can also use we can interchange them in some design scenarios that do not maybe not favorable. So you can interchange them, but the best way is to use a square column for square footing and rectangular column for rectangular footing. So we have loads for calculating the area of footing. Loads at serviceability limited are used. These represent the critical of the following. So we have dead load plus live load, which we use 1 point. So the factor of safety is 1, same as a dead load with windward load. We still use the same factor of safety, but when you're combining both dead load, live load, and wind load, when we reach to live load, we tend to reduce it by 0.8, and also we reduce the wind load by 0.8. So let's just proceed that the bearing pressure under the base of the foundation should not exceed the safe or allowable bearing pressure of the soil. So this basically they are trying to say that the pressure under the base of the soil should not be exceeded by the pressure exerted by the surface by your structure or by the structure you are designing on. Then typical allowable bearing values for various soils. You can see if maybe you have a rock or a soil, this is the type typical bearing values. However, you should not rely on this fully. You should always rely from the geotechnical reports or soil reports, which will give you these bearing values to use them for your design. We have design considerations, what we actually design for. So we have structural checks, this direct shear. So what we check after design, we check for direct shear, that's a one-way shear. We also check for punching shear, which is a two-way shear around the column. I'll be demonstrating all this, and then have reinforcement based on the bending and the shear force. So what this forms part of our design for the reinforcements. Then we have design steps. What are these design steps that we actually follow? We have established column loads and factor them. Uh, then that's both the live load and dead loads. And then select trial footing size. Just make an assumption of your footing size. Check soil pressure distribution, compute bending, and the critical section. So we'll be looking all these with examples, with real life example, and then provide reinforcement as the main bars and distribution skills. Check direct shear at D from the surface of the column. Check punching shear at perimeter, that's 2D. And then detailed reinforcement, anchorage, and cover spacings. So just design and give you. So these are the design procedure of a pad foundation. So design consideration, you can see how our pad looks like assume linear distribution of soil pressure across the base. So you can find that when we have just axial moment or just vertical moment, you have a uniform pressure exerted by this below here. But if you have a moment, if you add an additional moment here, you have kind of this type of pressure whereby pressure is exerted higher on one side and lower on the other side. So we'll be seeing the formulas to calculate all this. However, in real example, this is how pad foundation pressure is usually exerted, but you don't assume this shape because it will not be practical in calculating. It will be very complicated in designing. So we just assume these two, and this is what we work with. Having said that, for the cover, because of the adverse conditions under the soil, we can use 75 when we haven't done blinding. But if you do blinding for your, let's say for your excavated foundations, then you can use, if you already did a cover, you can use, if you already did blinding, you can use a cover of not less than 50 mm. Now, design considerations, this one I've already mentioned. And what, okay, this is just use grade concrete grade of, this is usually recommended as the concrete grade. And what do we have? Your pressure distribution. You can see how now the formula is being distributed. You just find B and D, and we have this the height of your pad foundation. So to get pressure will be P, will be N, this force over area. Area will be B and D. So you can find it here. This is how you calculate the pressure below the surface of the soil. So what about when you come to this? So when we are looking at pressure distribution in soils, whereby we have now moments in addition to actual force, this is the formula we'll use, that's Pn over A minus the pressure of this moment, because as you can, if you exact pressure and then you try to turn it over this, it will be less the pressure for the moment. So, and how do you get your I here is BD, this B and over D, which is the area divided by the moment force. That's My. You subtract from the initial pressure, you get the pressure at P1. For the P2 now, you just add it here. And that's how you get pressure distribution for a column that's subjected both on axial load and in moment. That's axial load plus moment. So let's proceed. And what about eccentricity in loading? That's N and E. This is how you calculate the eccentricities. You can just see here. Since the soil is weak in tension, the part in tension is ignored in design if possible. Never take E is greater than D over 6. So that is what I want just to illustrate here. This is what we mean. Then eccentricity in loading, this is just a repeat of that. So tie beam, this is how a tie beam is usually designed. Sorry. So I wanted just to zoom so that we can have a look at that. So these are column, these are footing, this connecting column, this column, footing reinforcement. You can see how it's being detailed. So let's just proceed. So design for moment reinforcement. If you're just designing for axial load, this is how you work about it. So the pad acts as a cantilever, loading by pressure, that's P, and supported by a column. So the moment in the pad is maximum at the face of the column. So you can see the, so this is what they mean. For moment calculations and design of reinforcement, use the ultimate load, not the service loads. So this is just the design consideration for when design for moments and reinforcements. So to get this P, you just say that's A over this area here, and the pressure will be greater near this column here. So if that's the case, then this is how it can be designed. So to get force will be P times the area. That's pressure times area to get the entire force here. So that's P BL. What's B here? This is our B and this is our L. And how do you get L? L is given by D minus H. That's the this size of the column over 2. So this is how you calculate your force, and then for the moment it's FL over 2, and you get it in kilonewton meter. To get K, you can get from this common formula here, and then to get Z, you have it here. Then from here, you can be able to calculate your area of steel required. So repeat the same for the short direction so that you get your reinforcements. Check for direct shear. This is how you can check for direct shear. This is the formula. You have L, this is the formula VP times area, and then P by L, and all those are here, how you can get them. B, this is the B, and then L, this is the L, how you calculate L in this case. So you have all the parameters here. You can just pause a bit and just understand this formula. So check for punching shear is almost same as checking for direct shear, and this is the formula that you calculate. You can simply look, it's a self-explanatory, all formulas are here, and everything is just illustrated as you can see. So having said that, let's just proceed to design steps for pad footings. So let's assume a suitable value for H, that's H, depth of the column, and the effective depth D as a guide. Assume a shear stress of 0.5 VU. So if you assume this and you want to calculate your depth will be N over NU divided by column perimeter times UV. So this is the formula for calculating the effective depth. And then round H. H you just simply get, now H will be equals to D, this effective depth which you calculated here, plus cover plus diameter of the bigger rebars or the main reinforcement rebars. So if you add that, you get your H as this minimum, and then note that NU is the ultimate design load. So calculate the planned size of the footing B and D using the allowable bearing pressure and the critical loading arrangement. That's NS only, and N and moments at serviceability. That's load at serviceability, moments and moment at serviceability. Serviceability limit state only. So that's how you calculate, use that to calculate the size of your footing B and D. Just remember this. Having said that, so the design steps here, I can continue. So after getting your B and D, you proceed to step number 3, which is calculate the bearing pressure associated with the critical loading arrangement at the ultimate limit state P. So determine the reinforcement required to resist bending in the two directions. Check the direct shear at the critical section, that's at 1D from the face of the column. Check the punching shear at 1.5D from the face of the column. Draw the plan and the section as shown in the dimensions of the reinforcement. So this is how you can draw now your reinforcement. So you get your D, you get your B, and then you can also design your area, and this is how you detail your base foundation. So you can just see reinforcement and footing. This is how we detail them. So this is just you can just read through and just get the details, and that's the end of our session part 1. In the subsequent video